Hello guys, and welcome to another video. In this video I'll discuss about the design of an staircase. Let's start with the design step of an staircase, and after this there will be a numerical of it. So the very first step is to calculate the effective length of a stair using the clause 33.1. There are three cases and according to which the effective length of stair will be determined, and I will discuss this in the numerical portion also. Similarly, the second step is to calculate the effective depth of stairs by using the ratio of effective length to effective depth and taking the ratio value as 30 to 40. Okay, any of the value between these two ranges. Similarly, third step is to calculate the total load acting on the stairs. Here a little bit different than that of the slab. Okay, the load acting on the stair is calculated separately, that is for the landing portion and the going portion. Step 4 is to calculate the maximum bending moment and shear force, and step 5 is to check the depth against bending moment, whether the depth calculated from here is sufficient against the bending moment calculated over here. Similarly, step 6 is to calculate the area of steel for maximum bending moment, and the area of steel can be calculated by using a formula from the Annex G of IS 456, considering a under reinforced section. Step 7 is to check for the shear force. Okay, that is calculating the shear stress using the shear force and comparing with the permissible shear stress. Generally in staircase we do not provide shear reinforcement, and the shear stress should be resisted by the shear strength of the concrete, so that we have to check for the shear force. Step 8 is to check for deflection. Okay, using the deflection criteria, that is L by D should be less or equal to alpha, beta, gamma, lambda, delta, where alpha, beta, gamma, lambda, delta are the basic values calculated from the code using the graph. Similarly, step 9, check for development length. Okay, development length is equal to phi into sigma s divided by 4 into tau bt. This is from the code. I will show in the numerical also. Step 10, reinforcement detailing with the distribution bar. Besides this step, we should also find out the riser and tread. Okay, and for general purpose we take the riser height as 150 to 175 mm, and considering this we take the tread width as 200 to 250 mm. We should also know that the number of tread is equal to number of riser minus 1, that is the number of tread is always less by 1 than that of the number of riser. So here is the numerical. Design a staircase over a length over a wall support to carry live load of 2.5 kN per meter square and the floor finish of 1 kN per meter square. The floor to floor height is 3.3 meter. Use M20 concrete and tor steel. So this is the first step. Okay, I didn't include this in the design step of staircase because this is simple architectural calculation. Okay, this doesn't have any structural importance, so these are to be considered for the purpose of comfort and architectural view. So simply let riser, that is if this is the staircase, okay, this height is known as the riser. Let riser 150 mm. So this is generally taken between 150 to 175 mm. Similarly, number of riser 3.3 divided by 0.15, total height of the staircase and per riser. Then the number of riser can be calculated by using the total height divided by riser height. So this comes as 22 numbers. So this number of riser is throughout the story height. So number of riser per flight, it will be 22 divided by 2, so it comes as 11 NOS, 11 numbers. Similarly, number of tread per flight, the number of tread is less by 1 than that of the number of riser, so 11 minus 1, this comes as 10. And let tread, this is generally taken between 250 to 300 mm. Then total going, this is the total length per flight, 10 into 0.25, so 2.5 meter. As you can see, this is the total going. Okay, from this to this, from the first riser up to the point before landing, it is the total going. I hope you understand this point. So this is the plan of the staircase. and the total going is 2.5 meter, providing 1 meter of landing. In generally for the residential building it is taken as 1 meter. Now we go to the main design procedure. Step 1, to calculate the effective length. Okay, and L effective is equal to 4.5 meter. So if we consider from clause 33.1 of page 63 from IS 456, so for our case we'll use the case C, that is where the landing spans in the same direction as the stairs. They shall be considered as acting together to form a single slab, and the span determined as the distance center to center of the supporting beam or wall, and the going being measured horizontally. So the effective length is measured as like this: 2.5 plus 1 plus 1, that is the total landing length on either side. So 2.5 plus 1, this comes as 4.5 meter. Okay, so the effective length is 4.5 meter we have found. Step 2, to determine the effective depth, and we can use the ratio of effective length to effective depth as 30 to 40. So I am taking 30. D is equal to 4.5 divided by 30, this comes as 0.15 meter, taking a greater value, so I will take 0.16 meter, and this will be equal to 160 mm. Adopting a bar size of 12 mm and taking clear cover as 15 mm. Okay, as we know from the code, up to the bar size of 12 mm the nominal cover can be reduced by 5 mm for a mild exposure. Then total depth is equal to effective depth plus half of bar size plus clear cover. So finally we get this as 181 mm, taking a greater value, so 185 mm, taking as a multiple of 5. Okay, simply. Then effective depth will be different because the effective total depth is different. So 185 minus 12 by 2 minus 15, that is total depth minus half of the bar size minus effective cover. Then we get this as 164 mm, which is the effective depth. So we have found the effective length as well as the effective depth. Now step 3 is to calculate the total load. So it is little bit different than that of the slab and footing, because we have to consider the waste slab here. So I will show you. Now the first step is to calculate load on landing. Okay, because the landing is simple structure, and whereas the going or the riser portion and the tread portion is little bit different. Okay, as you can see, suppose this is the landing, then the load acting on it will be simple like this. Then the very first thing, live load 2.5 into 1, we are considering a per unit width of a section, so 2.5 into 1, this comes as 2.5 kilonewton per meter. Similarly, floor finish 1 kilonewton per meter square into 1 meter, this comes as 1 kilonewton per meter. Self weight of the landing, which is equal to gamma concrete, this is the unit weight of concrete, 25 into depth of the landing 0.185 into 1, this is the total depth into width, so 4.625 kilonewton per meter. Total load on landing is equal to 2.5 plus 1 plus 4.625, so this comes as 8.125 kilonewton per meter. Factored load multiplying with the partial safety of factor, so this comes as 12.875 kilonewton per meter. So the difference is here, that is the load on stairs. There is simple mathematical calculation to find the total load. The live load will be simple, that is 2.5 into 1, this comes as 2.5 kilonewton per meter. The difference is in calculation of the self weight. Floor finish is equal to 1 into 1, this comes as 1 kilonewton per meter. Now weight of waste slab and weight of steps. So I will calculate this in different forms. The stairs are provided in this way. Okay, it will have like this, and it will have a waste slab over here. So I will calculate the weight of this waste slab differently and the steps differently. This is a portion of a stair, this is the riser and tread, and this is the waste slab. Okay, now if I consider for a single step and its waste slab portion, self weight of waste slab, it is simply a rectangular portion. So gamma, this is the concrete, unit weight of concrete, into D, that is the depth of the waste slab, into T square plus R square, because if we see, this is right angle portion. So if I have to find this portion, which is the hypotenuse of the right angle, I can use the formula, that is Pythagoras theorem. So T square plus R square, I will get this portion. Suppose let me write this as L, then L is equal to, or L square is equal to T square plus R square, and taking this square over here I will get this term. Okay, so gamma concrete into D, that is the depth, into length of this portion, so under root T square plus R square, T is the trade width and riser width, into 1 by T, because I am doing it per trade. Okay, so the self weight of waste slab per trade, then we get the value of the self weight of waste slab. Similarly, self weight of the steps, gamma, this is the unit weight, into 1 by 2 into R into T, because this is a triangular portion, so the area of this triangle can be used by half of the, or 1 by 2 into height and breadth of the triangle, so 1 by 2 into R into T into 1 by T, because I am calculating the self weight of the steps per trade. Weight of waste slab is equal to 25 into 0.185, which is the depth, into hypotenuse, so 0.25 square plus 0.15 square, this is riser, this is trade, into trade width, this is 0.25, so this comes as 5.39 kilonewton per meter. Similarly, weight of steps 25. Okay, so this is the unit weight of concrete, into 1 by 2 into, this is the area of the triangle, that is trade and riser, into 1 by 0.25, which is per trade, so this comes as 1.875 kilonewton per meter. Finally, total load on stair or steps is equal to 10.765 kilonewton per meter. Factored load is equal to 1.5 into 10.765, and this comes as 16.475 kilonewton per meter. Step 4 is to calculate the maximum bending moment and shear force on the stairs. This is the load acting on one of the flight, this is the landing portion, and these are the other landing portion, and this is the going portion. Okay, the load acting on the landing portion is 12.1875 and 16.475 in the going. Sometimes the load acting on the landings may be different. Okay, so in that case the load which is greater on landing is to be taken for the calculation of shear force. Now Vmax, this is the maximum shear force, and for maximum shear force we have the formula W into L by 2. For the shear force, we will take the sum of shear force acting on landing as well as the going portion. For landing portion, the value of weight W is 12.187. Total length of the landing is 2 meter. Okay, this 1 meter and this 1 meter. If suppose the value of the other landing was 18, suppose here, then we will be taking 18 here. Okay, we will take the greater value, plus the load on the going portion, which is 16.475, and the total section length is 2.5 divided by 2, so you can just remember this as WL by 2. So we get this value as 32.37 kilonewton. This is the shear force acting on it. So now for maximum bending moment, which occurs at the mid span, okay, at this point the load acting in this portion will be the landing load, okay, the load on the landing, as well as this much portion of the going, okay, load of the going, this half portion. So this distance will be 2.5 by 2. Okay, now from this point if I consider the moment, then mx is equal to minus 12.1875, because it is in anti-clockwise direction, into 1, this is the total width of the load acting, into 2.5 by 2 plus 1 by 2, this 2.5 by 2 plus half, because this load will be acting at this point at the mid of this section, so 2.5 divided by 2 plus 1 by 2. Similarly for this section the load is 16.475 anti-clockwise to this point, into 2.5 by 2, first consider this point, okay, 2.5 divided by 2, and it acts at the midpoint of this section, so 2.5 by 4, this distance will be 2.5 divided by 4. Now there is a shear force acting at this end, so for which it will be a clockwise, and we have value 32.375 into the distance is 1 plus 2.5 by 2, so 2.5 plus by 2 plus 1. Finally we get maximum moment as 38.88 kilonewton meter. Okay, you can also consider from the either side. Now maximum moment, we have to check whether the depth is sufficient to resist this maximum moment. Now for Fe415, that is torus steel, we have maximum moment is equal to 0.138 FCK BD square. Okay, this is converted from 0.36 FCK B into D minus 0.42 XU. You have to substitute the value of XU for Fe415 in terms of D and you get this equation. We have maximum moment as 38.88 and converting into Newton mm, we get 38.88 into 10 to the power 6 is equal to 0.138 into FCK 20. We are considering a unit with section that is 1 meter, so converting into mm we get 1000 into D required square. We have to check whether the depth calculated previously is sufficient or not, and this comes as 118.68 mm and the calculated value is 164 mm. So we get that the required depth is less than the value of depth provided, so it is okay. Step 6, to calculate the area of steel. As I said, we will use a formula from Annex G of IS 456. You can find in the code. Mx is equal to 0. Remember, we are considering under reinforced section, so we are using this formula. Mx is equal to 0.87 FYAST into D into 1 minus FYAST by FCK B into D. You can find this in the Annex G. Now substitute the value 38.88 into 10 to the power 6 is equal to 0.87 into 415 into AST into 164 effective depth into 1 minus 415 into AST by 20 into 100 into 164. We get the area of steel required is 722.77 mm square. Now let us check whether this area of steel satisfies the codal provision or not, and according to the code, the minimum area of steel to be provided is equal to 0.12% of the gross area of section. Remember, this is the overall depth. So 0.12 divided by 100 into 1000, this is the unit width, into 185 overall depth. This comes as 222 mm square. So we find that the area of steel provided is greater than that of the area of steel minimum. So it is also okay. Now let us find the spacing of the bars to be provided in the section. So for spacing, we have formula as spacing is equal to width of the section divided by area of steel provided divided by area of individual bar, and we are providing a bar of 12 mm for which the area of individual bar will be pi by 4 is into 12 square, and this comes as 113.097. We are considering a section of 1000, that is 1 meter. Then we get this value as 156.49 mm. The spacing between the bars should be 156.49 mm. Now let us check whether this satisfies the spacing from the code or not, and spacing should be less or equal to 300 mm or 3 times of the effective depth, providing 12 mm bar at 125 mm center to center spacing. The closer the spacing, the more stronger the section is. After providing this size of bar, the area of steel provided will be different. So area of steel provided is equal to 1000 divided by 125 into 113.097. We are just interchanging the value over here. We have spacing as 125, section as 1000, and area of steel of individual bar is 113, and just we are providing or calculating the area of steel provided. So we get this as 904.77 mm square. Step 7, that is to check for the shear, and we have to find the shear stress acting, for which shear stress maximum is equal to Vmax by BD, and we have calculated the value of shear stress as 32.37 into Newton. We get 32.37 into 10 to the power 3 divided by 1000 into 164, and this comes at 0.202 Newton per mm square, which is less or equal to 0.28 Newton per mm square. This is also from the code. Okay, this is the minimum shear strength of concrete for M20 grade. We are checking with this value because we are not going to provide any shear reinforcement in these stairs. Less or equal to 0.28 Newton per mm square. This is the design shear strength of concrete, and we assume that the shear strength of the concrete should be sufficient to withstand the shear stress acting in the stairs. This is table number 19. For M20 grade of concrete, the minimum shear strength of concrete is 0.28, and the shear stress acting on the stair is 0.202 Newton per mm square, which is less than that of the design shear strength of the concrete, hence no shear reinforcement has to be provided. That is, we conclude that the shear strength of the concrete is sufficient. Step 8 is check for the deflection criteria, and for deflection criteria we have from the limit state of serviceability, L by D it should be less or equal to alpha, beta, gamma, lambda, delta. Okay, and for which let us find the ratio of length to depth, that is 4.5 divided by 0.164. This comes as 27.43. Similarly, alpha, for the value of alpha, basic value up to the effective depth ratio, or for a span up to 10 meter, a simply supported case, then we will take this value as 20 because the span is less than 10 meter. So the value of alpha is taken as 20. Similarly, for value of beta, the span above 10 meter, okay, as the span is not above 10 meter, so we will just take the value of beta as 1, as we don't have to multiply by any of this. Similarly, for the value of lambda, we have to use the point in D depending on the area of compression reinforcement. So we are not providing any compression reinforcement in the stairs, so we can directly take this value as 1. Okay, so you can also find this from the graph. Percentage compression reinforcement as 0, so the modification factor value is taken as 1. Similarly, for delta, we have to use this graph and the ratio of wave width to flange width. We are not providing any flange section, so the ratio of wave to flange width will be 1, and for which the value of reduction factor will be 1. So alpha as 20, beta as 1, lambda as 1, and delta as 1. But for the value of gamma, let us read out this point C. Depending on the area and stress of steel for tension reinforcement, the value of A or B shall be modified by multiplying with the modification factor as obtained from figure 4. Okay, this is the figure 4 at page number 38. As it says, the percentage tension reinforcement, we have to take the modification factor, and before that we have to find the value of Fs. For gamma is equal to, we have to find the percentage tension reinforcement. So AST provided by BD is equal to 904.77 divided by 1000 into 185. The area of steel provided is this, so we get this value as 0.489%. Similarly, for the value of steel stress of service load, Fs is equal to 0.58 into Fy into AST by required divided by AST provided. So we can substitute this value. Area of steel required was calculated as 722.7 and area of steel provided is 904.7 as 192.26 Newton per mm square. Then from figure 4, page number 38. So from figure we have to take percentage tension reinforcement, which is 0.489%, and the value of Fs is 192.26. So the value of Fs lies between these two curves, that is 190 and 240. Similarly 0.489, so it lies somewhere here. Now if we interpolate this value, we get the value somewhere at this point. Okay, so 0.489 and this value. So taking gamma as 1.6, then alpha, beta, gamma, lambda, delta is equal to 20 into 1 into 1.6 into 1 into 1. So this comes as 32, and the value of L by D was found as 27.43, which is less or equal to alpha, beta, gamma, lambda, delta. So the deflection criteria is also satisfied. This is okay. Now step 9, that is development length. From the code we have the value for LD as phi into sigma s divided by 4 into tau BD. Phi is the bar size 12 into, and phi s is taken as 0.87 into Fy, that is 87% of yield strength of the steel, and 4 into 1.2 tau BD. For M20 grade it is 1.2, and 60% can be increased for the deformed bars. It is also from the code you can find. This comes as 564.14 mm. So this is the development length required for the stairs to transfer the load from steel to the concrete. Step 10, this is the detailing of the distribution bar. Previously we found out the details of the main bar. Now let us check for the distribution bar, and this is from class 26.3.3 B I and II, page 46 of IS 456. For distribution bar, spacing is taken as 1000. This is the section width of 1 meter. divided by 222. This minimum area still to be provided. We have found AST minimum as 222 mm square. So AST minimum divided by area of individual bar. So providing a bar of 12 mm, then it comes as 113.097. So finally we get 509.44 mm, and this value should be less than this two value. This is also from the code, that is less or equal to 450 mm and less or equal to 5 times of the effective depth, that is 164, which comes as 820 mm. And for main bar 3D and distribution bar 5D, this value. Now we will provide a value which satisfies both of these conditions. For now this is not satisfying this condition, so let us provide distribution bar with this suitable spacing. So provide 12 mm diameter bar at 300 mm center to center. So now this satisfies both of the condition. The last step, that is the 10th step, is the reinforcement detailing. So these are the reinforcement detailing. Okay, the line here, this line represents the main bar 12 mm die bar at 125 mm center to center, and above which the distribution bar are provided. Okay, this circle represents the distribution bar. Similarly, development length is provided over here. And the bar are embedded into the support members like wall or beam, and this should be greater or equal to LD by 2, that is half of the development length. This is also the reinforcement detailing. Okay, thank you.